For those of you who don't know about the ATI, it's essentially a public intermediary working alongside the government and the aerospace industry to set the technology strategy for the sector and to fund R&D in the sector. So very exciting, the work we do. So today's presentation is called Destination Zero, the Technology Journey to 2050. And what I'll be talking about in this presentation is the pathway to net zero in aviation by 2050. And the second part of the presentation is about what that means for electrification in aviation, electrical propulsion, and electric motors, which is really the topic of the conference today. So my colleagues from FlyZero couldn't be here. So FlyZero, for those of you who don't know, was a ATI-funded 12-month project looking into the feasibility of zero carbon emission aircraft by the end of the decade. So, so I stepped in for them because they couldn't make it. So what I'll be talking about is a combination of the ATI strategy and some of the FlyZero findings related to electric propulsion. So the ATI technology strategy, so we launched a refresh strategy early this year in April. If you haven't already downloaded this, please do. It's an interesting read. This document essentially defines our priorities, sets out our objectives, and quantifies our impact to the sector. So please have a read through. It includes roadmaps. So we have 3 roadmaps, one for zero carbon emission aircraft technologies, one for ultra-efficient aircraft technologies, and one for cross-cutting enabling technologies. So cross-cutting enabling technologies are those that enable the ultra-efficient and zero carbon emission technologies, including design and modeling methods, manufacturing technologies, and through-life support. So quite an interesting read. Please do go ahead and read those. So what are our key strategic objectives? So this for the ATI. So what are the ATI's strategic objectives? Firstly, to position the UK to be a leader in the sector, in the aerospace sector, to achieve net zero in aviation by 2050. Secondly, to accelerate the introduction and adoption of technologies that deliver net zero carbon emissions. And thirdly, to secure and enhance UK industrial competitiveness. So essentially, in a nutshell, that's what we are striving for as a company, as an intermediary between the government and the sector in the UK. So the ATI identified what we call drivers of change that will underpin the evolution of the aerospace sector in its journey to achieving net zero emissions, net zero carbon emissions by 2050. The first of these is about taking risks in technology development. Many of the technologies to address sustainability in aviation are going to be radical and high risk. It's very important to be ambitious and accept more risk in technology development to be able to deliver these technologies to address sustainability in aviation. The second of these drivers is about continual efficiency improvements to reduce in-flight energy usage and also increase profitability for operators. And this could be improvements in aerodynamics, it could be reduced weight for many of the systems, or improving the energy efficiency of these systems. And this is quite important because it's beneficial regardless of the energy source that is used, whether it's today's kerosene or jet fuel, or battery as energy source or hydrogen as energy source, energy efficiencies will benefit aircraft regardless of the energy source. The third of these drivers is about adoption of sustainable aviation fuels. BioSAF, Bio-Sustainable Aviation Fuel, its production and usage will increase rapidly, but it's limited by the production capacity. And that's a critical challenge going forward because today the SAF pathways don't look too scalable. The fourth of these is about disruptive zero carbon emission technologies that are going to disrupt the market. FlyZero, which I mentioned, looked in detail into all of these zero carbon emission technologies. And their findings indicate battery electric powertrains can power flights at the smaller end of the market segment in the sub-regional space. But as you increase the size of the aircraft, you need to go to other fuel sources. So hydrogen fuel cell powertrains will power regional aircrafts, regional-sized aircraft. And beyond that, for larger aircraft, you need to go to hydrogen combustion. So these are the drivers of change to be aware of, and this will help achieve the net zero targets in aviation. So how do we actually go about achieving net zero by 2050? So this chart here shows global aviation CO2 emissions over time. So if you do nothing, then aviation is going to be responsible for about 38 gigatons of carbon dioxide emissions by 2050. So how can we reduce CO2 emissions and achieve net zero? So through a combination of ultra-efficient aircraft technologies, zero carbon emission aircraft technologies, and optimized operations, we can abate about 2.5 gigatons of CO2. BioSAF and other market-based measures can reduce CO2 by another 8.3 gigatons. That leaves us with a big chunk of CO2 emissions relying on other market-based measures and synthetic SAF. And given that these SAF pathways today aren't too clear in terms of scalability, it's quite risky. We may not be able to actually achieve net zero by 2050. So what's required is the acceleration of these ultra-efficient and zero-carbon technologies to enable the introduction and adoption much earlier and the entry into service of the aircraft which uses these technologies much earlier. So we've got entry into service of the regional ultra-efficient, narrow-body ultra-efficient, regional zero-carbon, narrow-body zero-carbon, and wide-body ultra-efficient, and wide-body zero-carbon. So these are what we know based on the scenarios today. But if we have to really accelerate and ensure achievement of net zero, we need to act with urgency and accelerate the deployment of these technologies. It could potentially involve we try and bring the introduction of the wide-body zero-carbon much earlier, and that could have a significant impact. So the zero-carbon emission aircraft roadmap, which you can find on our website, has a number of technologies that are required to enable zero carbon emission aircraft. And one of the critical and key technologies is electrical propulsion. And we've got that, you can see that here, high power motors and drive systems for electric propulsion is one of the key technologies. And in the next few slides, I want to talk about some of the highlights from FlyZero and the findings related to electrical propulsion and electric motors. So FlyZero did a detailed study of electrical propulsion system for the regional aircraft, and this based on a fuel cell system. So it's a fuel cell electric powertrain. So the sort of powertrain consists of a fuel cell system, which is made up of a fuel cell stack and a balancer plant, followed by DC to DC converter, inverter, motor, a gearbox, and a propeller. So this, 6 of these can actually enable a regional concept aircraft, which can carry about 75 passengers up to 800 nautical miles. So this is the architecture that they worked on. FlyZero came up with some performance targets for the whole electrical propulsion system, and also the targets for the subsystems. By 2026, the target for the electrical propulsion system is to achieve a power density of 1 to 1.5 kilowatts per kilogram. And what that means for the motor is that the motor will need to achieve 13 kilowatts per kilogram, which is pretty high. And the challenge is even more daunting going to 2030 to achieve a power density at the system level of 1.5 to 2 kilowatt per kilogram. You need an electric motor power density of 23 kilowatt per kilogram. And to achieve, ultimately, by 2050, a electrical propulsion system power density of 3 to 3.5 kilowatt per kilogram, you need an electrical motor power density of 25 kilowatt per kilogram. So you can see that there's less of a drastic change between 2030 and 2050. This is because the electrical propulsion system power density is largely reliant on the improvement in the fuel cell system power density and less on the motor at that, in that time frame. So FlyZero also looked at the mass breakdown in the electrical propulsion system, and what they found was the electrical powertrain accounts for almost 40% of the mass of the electrical propulsion system. And within the electrical powertrain, the motor and the gearbox accounts for 14%, and power electronics, including the DC to DC and inverter, they account for about 20%. So it's important to understand this because, if you can reduce mass, obviously, you'll increase the power density. That's one way of achieving the improved power density. They looked at electric motor topologies as well. They looked at a number of topologies and ranked them on a number of criteria, including the gravimetric power density, the volumetric power density, efficiency, power range, high-speed capability, the maturity of the technologies, both in terms of the technology readiness levels and manufacturing readiness level, the fault tolerance, and the production costs. And what they found was, ranking these topologies, there are 4 candidates that can satisfy all these criteria, and those are the PM radial, PM axial flux, PM dual air gap, and PM vernier. So those were the topologies that were selected. They also looked into the power density for the geared motor versus the direct drive motor. So this is a chart of the gravimetric power density versus speed. These 2 dots you see here, that's for the direct drive motors. And many of you are experts in electrical machines here, so as the RPM of the motor increases, the number of poles decrease, and this in turn results in reduction in the iron mass, the magnet mass, and the passive structural mass. And also increasing the fundamental frequency can give you an increase in the power density. So what they then did was to map the technology choices across the power density regimes. At the lower end of the power density regime, the suitable topology or technology was the direct drive PM motor. At the in the middle regime, the high-speed PM motor with a gearbox, And for very high power densities, um, direct drive superconducting motors were required. So this is a technology staircase diagram showing the impact of specific technology insertions on the system level, electrical propulsion system level power density. So for the 2026 targets, in terms of the motor, advanced PM motors are required, along with additive and composite manufacturing to improve the power densities. So looking to 2030, this needs to be a significant jump in motor technology. Essentially, to achieve something like 23 kilowatt per kilogram, you need high temperature superconducting motors, along with advanced thermal management systems and cryogenic cooling systems. And for the ultimate target, you not only need a superconducting motor, but you also need a superconducting powertrain. So this is what they looked at, and eventually they also came up with a technology roadmap with a number of technologies across the kind of motor topologies required, the coil winding and magnet wire technologies, magnetic material technologies, and manufacturing improvements. I'm not going to go through these in detail now. Please do have a look at the technology roadmap. It's available on the website. But my key questions for the community here is, what other developments are required? Now we've got all this from the Lazaro work. What other developments are required to achieve the power density targets and to accelerate the achievement of these targets? And how can we ensure accelerated development through academia and industry, including the pull-through from the low TRL research from academia into industry, and cross-sector participation to enable aerospace standard high power density propulsion motors? So in conclusion, the Fly-Zero research shows high motor power densities can be achieved through specific technology choices, such as the dual air gap permanent magnet, high-speed options with gearbox, use of composites for lightweighting, and superconducting motors. So the UK has an opportunity to build on its strengths. Clearly, there's significant strength in electrical machines, especially considering all the work that's happened in automotive, and a very strong academic research base as well. So the UK needs to build on these strengths to accelerate the development of aerospace standard high power density propulsion motors. And these motors, these motor technologies can then enable hydrogen fuel cell electric powertrains for future zero carbon regional aircraft and beyond, as we continue to push the power densities. And accelerated development of the zero carbon emission aircraft technologies will not only help achieving net zero in aviation by 2050, but also create significant market opportunity for the supply chain and economic opportunities for the UK. So I'd like to just take a moment to invite you all to the ATI conference, which is happening in November at the Walks Conference Center in Birmingham. It's a 2-day event. I'm part of the working group which is looking to organize this conference, and I can tell you that we have a fantastic lineup of speakers from across industry and academia and other sectors. So please do join us, and we need cross-sector participation to really achieve net zero targets in aerospace. So please get in touch with us, visit the website, you'll find more details, and please do engage with me directly if you want to discuss opportunities for electrical propulsion or electric motors in aerospace. Thank you.